All right, calculus, as we move on into the second part right here of section 5.1, we're now going to start talking about how we use rectangles to approximate the area underneath a curve when those subintervals that they're giving us are going to be regular. In the previous problems that we did, like this one right over here, you can see that those x values aren't really following any set pattern, although here I had to worry about midpoints, but here these x values were totally random. But in most of the problems that we're going to see, at least I think in this section, we're going to be dealing with a function that is explicitly defined. Like you can look ahead right here and realize we're going to do an example right here where I actually gave you the equation for f of x. We're going to do a simple one here in a minute where f of x is equal to x squared. That wasn't the case in the previous few problems when we were just given random values within a table. So, as we start diving into regular subintervals right here, we're going to be doing, let's see, in this example, the same function here, f of x is equal to x cubed, in a few different ways or a few different cases right there. Sorry about that, everybody. Okay, so what's going on with this one right here? I'm all over the place. All right, gotcha. Now, what I think we're going to do here, just because it's our first example where we're working here on regular subintervals, I am going to take the time to go ahead and graph this function. Now, I want to stress to everybody, graphing is really not a very efficient problem-solving method. So I'm just kind of helping you do this to get your feet wet here, everybody. But this is not a method that you should be falling back on for most of these problems. So the function we're dealing with right here is f of x is equal to x squared. And we were looking on the interval right here, starting at 0 and ending at 3. So I'm going to go ahead and draw probably, definitely, a really stretched out version of this graph right here. This is going to be way wider than it probably would be in real life. But this function here, I tell you what, I want to focus just on what's going on with our x values here and not even pay attention to what the function itself is. So in this problem, we're doing an interval here from 0 to 3. This value right here, the left endpoint of our interval, is what we're going to be calling a throughout the course of this chapter. B then is going to be the right endpoint of your interval, which again in this example is going to be 3. The overall width of the interval then is going to be this right endpoint minus this left endpoint, which in this case is going to be 3. Now, a couple of other pieces of notation that we're going to do here. N, in general, guys, is going to represent our number of rectangles, and that is normally going to be given to you in each problem. Now, as I think about this one right here, I'm asking you to find L6, which means that in this particular example, n is equal to 6. Now, I'm going to use that information in just a second, but I want to talk about what we call making the partition of this interval. So to do this, I've got to be specific for this one particular problem. Now, we're dealing with a curve that is starting, let me see here, guys, I'm going to go to purple, I think, like I was doing before, is starting right here at an a value of 0. So right there at 0, guys, that's what we call a. It is also what we call x naught. That's a notation that we're going to be using in a minute here and also later on in this chapter. Now, this interval goes a certain amount and it ends over here on the right at a value that we normally call b, but it's also going to be called x sub n. And we'll explain that a little bit more. So a or x naught, that's where you begin on the left, and then b or x sub n is where you're going to end over here on the right. So there's your overall interval, and then we're going to partition that interval up into our subintervals. Well, again, we said in this example that n, the number of subintervals we're dealing with, is going to be 6. That really could be any number, but okay. So what am I going to do? I'm going to try, and I'm just eyeballing this here, guys. I'm going to try to bisect this interval right here from 0 to 6, and I guess I can go ahead and start labeling this. That's at 0, and that's at a 6 right over here, and we came up with a 3 right there in the middle, and now I'm going to attempt to trisect each of those intervals right there. Just guessing right here, but okay, no, this looks too big right there, but close enough. So I just realized I did that wrong. Sorry about that. That should have been, sorry, that 6 is not right. We ended this thing at 3. That meant that we had a 1.5 right there in the middle. Sorry about that, guys. And now we're at a 1/2 right here, a a 1 there, a 2 here, and then a 2.5 right over there. So we've kind of partitioned our overall interval here, which had a width of 3, into 6 subintervals. Now, what I think is obvious right here, guys, is the width of each subinterval. Each one of the 6 that we've drawn has a width here of 1/2. It might not always be so obvious. So let's talk about how we got that. Delta x is the notation that we're going to use here for the width of each one of those subintervals here. So I'll go ahead and just label one of those right here. Delta x is the width from one subinterval right here, or of width of one subinterval. And the way we found that here, guys, is we took the overall width of the interval from 0 to 3. That got us a width of 3. And we divided that then by the number of subintervals right here, which is 6. So a formula that would be really good for you guys to write down and hopefully to have memorized is that delta x is going to be given to us by taking b minus a, that's the overall width of the entire interval, and dividing that by n. So I think that would be a really good thing for you guys to box up and put in your notes, because there will be problems where a and b and n are given to you. You've got to figure out delta x. In fact, I think the problem we're about to start working on right here, you've been given a, you've been given b, you've been given n. Now, while we're at it, though, I want to remind everybody that when you've got a division expression like this, delta x is equal to b minus a divided by n, you could also swap the left side and the bottom of the right and get another true statement. So it is also true that n could be found by taking b minus a and dividing that by delta x. And that would be useful to you if there were ever a problem. And I think you guys have a worksheet coming up I gave you where this is the case. If you had a problem where you were given a and b and delta x and you had to figure out the value of n. I'm going to get rid of this arrow right over there. All right, let's do that. So I think those two formulas that I just put in a box right there would be helpful for you guys to have in your notes. Okay, so what's going on right here, guys? Really then, each one of these red values that I have on the x-axis right here is a subsequent x value. So this 1/2 is what we would call x sub 1. The 1 would be x2, the 1.5 is x sub 3, and x sub 4, and x sub 5. And then this x sub n, well, in this particular problem, it won't always be the case, but that is also x sub 6 in this example. All right, so that's good to know. Now, I'm going to be referencing those values here a little bit later on, so that's good to know. So what's going on here, guys? We've got the curve of y equals x squared. So now for the first time, I want to go ahead and draw that. And we know that this thing starts at the ordered pair 0, 0, and it's going to end at the ordered pair 3, 9. Now, I don't really care about getting this graph drawn super accurately, so I'm just going to choose a point right about there and say, okay, you know what? That is going to be a height of 9 right there. All right, so I'm going to draw a nonlinear function increasing at an increasing rate that looks something like that. And I don't think I drew that perfectly, but honestly, I really don't care. It doesn't matter that much. I just wanted it to be a curve. So now what we're going to do is we're going to talk about trying to find the area underneath this curve right here from x equals 0 right here to x equals 3 at the end. And we're coming up with an approximation for the area underneath this curve. And how are we going to do it? Well, we're going to start off by doing left endpoint rectangles. So if you understood the way this was explained in the first video, I think you can see what's going on right here. We're going to be drawing some left endpoint rectangles on each one of these subintervals. All right, and the first rectangle, this interval right over here, starts at x equals 0. Really, it starts at x naught and ends at x1 right there. So that quantity right there is going to get us the width of the first rectangle. And the height of the first rectangle, since we're doing left endpoint approximations, comes from this value over here on the left. So back to this problem, I'm going to go ahead and try to write kind of a generic formula here that's going to help you guys out in the future. If we're doing a left endpoint approximation for a random number of rectangles, which is going to be n. Well, here's the first thing I wanted to talk about that I haven't talked about before. In each of these subintervals, and there's going to be 6 in this example, but that number could change in future examples. What should happen, despite my bad drawing right here, is that the delta x value should always remain constant. And in this example, delta x is b minus a, that's 3 minus 0, all over n, which they told us was 6. And that's how we got 3 over 6, or 1/2, for the width of each one of those 6 rectangles. So when we go to find the area of each one of them, we're going to be multiplying base times height. So don't write this down. But L6 would be found by doing, let's see, the base of the first rectangle would be 1/2 times, let me just put height 1. Plus, the second rectangle has a base of 1/2 times height 2. And then the third rectangle has a base of 1/2 times height 3, plus so on and so on. Well, what you'll notice here is, unlike the last examples that we were doing in the irregular subinterval section, all of these rectangles have exactly the same base. So what are we going to do? We're going to factor that 1/2 out in front of this entire expression and then just add up all of your heights. Okay, so that's an important idea to have in mind here. So what I'm going to put for this formula, which we're going to put a big box around in just a second, is that we're going to begin by factoring out the width of each rectangle, which is what we call delta x. So that gets pulled out in front, and now in brackets, we're just going to add up the height of each rectangle. So the height of the first rectangle in this example is going to be f of 0, but more importantly, it is f, the original function you're given, evaluated at its left endpoint, which is always going to be x naught. So f of x naught is going to be the height of your first rectangle. We're going to add to that now. Let's take a look. Our second subinterval is right here, and its left endpoint is right here at x1. So, wrong way. So f of x sub 1 is the height of your second rectangle. Okay, and I think you can see where this is going. The third rectangle, its left endpoint is right here, so its height is going to be f of x sub 2. All right, gotcha. Now, what I'm going to do right now is something that math people love to do and students usually don't like. I'm going to get general. I'm going to put a ... right here because I don't really know how long this goes on. I know how many rectangles it's going to be in this example. We knew that n was 6, and sure enough, we end up with 6 rectangles. But we're trying to write a general formula right here that's going to be true regardless of the value of n. So the question now is, how far do we go? Well, if we take a look right here, the last subinterval is going to be this one right over here. And the right endpoint of that last subinterval is your b value, or x sub n. But what we want right here is the left endpoint of that subinterval. And its height is evaluated in this example by f of x5. But what I probably should have put in general here, guys, is if in this last one is x sub n, this value right here could also be called x sub n minus 1. It's 1 less than your last value right there. And that is the last spot where we're going to actually evaluate the height of a function right here. So the last height we're going to put here, guys, is going to be a plus f of x sub n minus 1. And that's going to be the last left endpoint that we're going to use in order to evaluate the height of that last rectangle. So I would put a big box around this right here, guys, because that's a formula you're probably going to want to use going forward. Now, if that looks like a lot to memorize to you, especially when you realize we're going to do an Rn formula and an Mn formula here coming up, I don't want you to panic, because I think that the more you get used to it, the more you're going to start to realize that this is something that you're going to learn conceptually and not really have to focus too much on knowing a formula for it. Okay, so let's dive back into this particular example here, guys. L sub 6 is equal to, let's get to it. Delta x, we already found on this example right here, is going to equal 1/2. That's the common width or base of every one of these rectangles. So we're going to have a 1/2 out in front. And now what we're going to do in these brackets is add up the heights of all of our rectangles. So we begin by evaluating f at x naught. And I want to remind everybody of what we said just a second ago. X naught right here is really the same thing as a, and in this problem, a was 0. So we're going to be doing f of 0 because that's the left endpoint of the entire interval. Then we're going to add to that the height of the second rectangle. Here's your second subinterval right here. We said we would evaluate that at its left endpoint, which is the x1 or the 1/2 right here. So the height of our second rectangle is going to be f of 1/2. Okay, the third rectangle now, this one right here, we're evaluating at the left endpoint. That's going to be x sub 2, or in this case, 1. So f of 1 gives us the height of our third rectangle. And now, I think we get the gist here, dot, dot, dot. I just want to put the last term that we're going to do here, guys. So the last subinterval goes from 2.5 to 3, but we're using the left endpoint here to evaluate that. So that is going to be f of 2.5 for that last height right there. So f of, I'm going to just write that as 5 over 2, and there you go. Now, there's two important things that I want to make sure everybody understands. And I say this is important, guys, because this is something you should be checking every time you get to this point right here. First things first, how many rectangles are we dealing with here? 6. That means that inside your brackets, you should be adding up the heights of 6 different rectangles. So even though I've got a dot, 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 let's count it out. We had a height of f of 0, f of 1/2, so that's 2. F of 1, that's 3. There would be a 1.5 here, that's 4. A 2, that's 5. And then here's your 2.5. So that is the 6 different rectangles that we were looking for. So that checks out. The other thing I want everybody to realize is the jump between all of the x values inside the function here where we're evaluating heights. And from 0 to 1/2, I hope this is obvious, we're adding 1/2. From 1/2 to 1, we're adding 1/2. From the 1 to the 1.5 that I didn't draw, that'd be plus 1/2, and so on and so forth. That amount that you're adding each time should be the same as this delta x, this 1/2 that you're putting out there as well. So those two things I just told you to check, the total number of rectangles matching this number right here, and also that your delta x being the amount that you're jumping each time, those two things should happen no matter which method it is that we're using. Left rectangles, right rectangles, or midpoint rectangles. Now at this point here, guys, we could go to the calculator to evaluate some of this stuff together, and I think I want to go ahead and do that with you, not because this one is super difficult, but honestly just because you're going to be doing the calculator most of the time in order to do this, because some of these are going to get relatively messy. So I'm going to go to my CAS with you, and I'm going to walk you through how I would do this. The first thing I would do here, guys, on every problem is define the function that we're talking about right here. So I'm going to define f1 of x, gotcha, to equal the function in question, which in this problem is just a nice simple x squared, and go, all right, here you go. That's what we've got. And now from here, the great thing about the Inspire CAS is that it understands mathematical notation. So I can type in exactly what we have written down on our paper right on this line right over here. I can start with a 1/2 and then use a big set of brackets to add up the heights of all of those rectangles. So let's do that, guys. We're going to begin with our height here of 1/2, which I'll just go ahead and type in as a 1/2, and we're going to multiply that by, and here we go, big set of parentheses now, and let's get to it, everybody. So probably should have done just f and not f1, but here goes. We have f of 0, that's the height of our first rectangle, plus, all right, this is going to get a little bit tedious, f1 of, I'll put a 0.5 right there, got it. And then plus, got to keep going with this, so f1 of 1, got it. Plus, all right, halfway home, everybody, we're going to do an f1 of, now we've got a 1.5, all right, plus boom, 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 f1 of 2, all right, and then plus last one now, we've got an f1 of 2.5 for that last one there. So I'm curious to see what that gets us and to see if we have an answer that seems reasonable for us right here. I got an answer of 6.875. So let me go ahead and write that down for right now, that L6 looks like it's going to be 6.875. Everything here would be square units. Now, before I box that up, let's take a look at what's actually happening right here. We're looking for the region under the area of the region underneath this curve. And if I were to ask you guys, what geometric shape does that seem to most closely mimic? I think everybody's going to tell me it looks like a triangle here. So just for fun, let me switch to green here, and let me just draw one big triangle here that looks like this. Okay, and the area of that triangle is going to be 1/2 times its base times its height, which is going to be 1/2 times a base from 0 to 3 of 3, and then the height here, guys, remember that f of 3 was equal to 9. Okay, that. 3 times 9 is 27. Half of 27 is going to be 13.5. So that's the area, for real, of the green triangle that I've drawn. So now the question is it possible that the area underneath, let me go back to blue right here, that the area just underneath the blue curve right here is 6.875. Well, I think that's probably not quite accurate, however, but I do think right here it makes sense that the answer we came up with has to be less than this 13.5 that we did here. So it's not too bad. The other thing, and you'll notice I didn't actually draw any of my rectangles in there, but I want to take a second real quick just to do that. If we think about what these rectangles look like, we're doing left endpoint approximations. So right there is rectangle 6. This is not something I would recommend you guys do on every problem because it's tedious and it doesn't really help you that much, but okay. There's rectangle 4. Here's rectangle 3. Rectangle 2 is going to look something like this, and rectangle 1 is actually non-existent. So as we look at it, I was going to ask you guys the question, does the area of those 6 rectangles added together seem to over-approximate or under-approximate the area underneath the blue curve? Well, that one looks like it's going to be under because there's all this gap right here above each rectangle that I'm missing. That's area underneath the curve that doesn't get counted in my rectangles. So here's what I'm realizing here, guys. The real answer here, the blue area, is less than the green area of 13.5. And my left approximation is actually less than the blue curve right there. So I actually feel okay about this answer here of 6.875. I'm pretty sure that it's not accurate, but it's less than the real answer right there, I'm pretty sure. And I think it's at least a good jumping off point for where we're at there. Okay, so that's how we do a left endpoint approximation with regular subintervals. Now, the second example we're going to do is a variation on that. And good news, everybody, this will take much less time than what we just got done doing. We're going to start with a formula right here now, just like we did on the last one, for a right approximation. So the formula here for r sub n is going to equal, and before we start writing it out, I want to go back to this messy diagram right over here. Okay, the good news is that our partition of the interval is exactly the same here as it was before. We're starting at 0, ending at 3, and we're taking 6 steps to get there, so the width of each step is still going to be 1/2. The width of each rectangle isn't changing, so we're still going to have a delta x out in front. And now in brackets, we're still going to add together the heights of all of our rectangles. However, things change just a little bit right here. And I tell you what, I am going to start a new page, but I promise I'm not going to redraw the entire thing. I'm just really going to redraw the x-axis right here and say, okay, hang on now. We're starting this thing right here at 0. which is also x naught, which is also a. We're ending this thing over here at 3, which is also x sub n, or really x sub 6 in this problem. That's also b. And again, we're cutting this thing up into 6 subintervals. Yeah, something like that, okay? So we've got a 1/2, a 1, a 3/2, a 2, and a 5/2 right here. Now, our first subinterval is right here, guys, from 0 to 1/2, but to evaluate the height of this first rectangle, we're now going to use the right endpoint to go up a little bit and determine the height of rectangle number 1. So the height of your first rectangle does not come from f of x naught, it comes from this value on the right, which is actually x sub 1. So that's why we're going to start this formula now with the height of the first rectangle is f of x 1. We're not using x naught here because we're doing right rectangles. Okay, the second rectangle then, everybody, the one that goes from 1/2 to 1, we use the right endpoint right there, which is 1, to determine the height of the second rectangle, kind of like that. So that one is using f of 1 for the height of the second rectangle. So plus right there, and that is the value x sub 2. I didn't write that one out. Sorry, guys. That's x sub 2 there, and there we go. X sub 3 is going to give us the height now of our third rectangle. So plus f of x sub 3, and I think you guys see what's happening. So I'll put a dot, dot, dot. And again, the question is, where do we end? Wrong way, sorry. So our last subinterval goes from 5/2 to 3, but because we're now doing right rectangles, we're going to use the right endpoint right here, which is x sub 6, or in general x sub n, to determine the height of that last rectangle, looking something like this. So back to my formula here, we're going to end this thing with f of x sub n. So that is a really similar expression to what we just came up with in the last problem right here, but we're basically just starting it and ending it at slightly different points than we did for that left formula we came up with a while ago. So back to this particular example now, guys, we're going to do r sub 6. Now, nothing has changed here. Our delta x is still going to be 1/2. That's the width of each rectangle. But now, to evaluate this function right here, guys, we're going to get its height at f of, and let's take a look, x sub 1 now. The first subinterval gets evaluated at a height of f of, that's going to be a 1/2 here. So f of 1/2 plus, and now we just keep adding a half to that. F of 1, that's the height of the second rectangle. The third rectangle is f of 3/2, or its height is that. We'll put a plus and a dot, 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 and a plus, and we end this thing now by measuring the height at f of, the right endpoint right here, is at 3. So f of 3 is the height of the sixth and final rectangle in this approximation. So again, I'm going to go to my calculator to do this because I did all of that work already, but if you guys are savvy with how to handle your calculator, I don't have to type all this junk in again. I can just hit the up arrow twice, hit enter, and just make one tiny little change right here. I'm going to go, let's see, all the way, well, let me stop right here. Instead of stopping at 2.5, I'm going to add to that at the end, now, here we go, an f1 of 3. And, probably worried some of you that I didn't do that, I'm going to get rid of the f of 0 at the beginning of this expression. So right there, let me take out that. Okay, and this expression should match what we have on our paper there. So I'll go ahead and hit enter now, and I got 11.375 for this answer right here. 11.375 square units for our value here of r of 6. Okay, so that answer is quite a bit higher than the answer we came up with here for L of 6. And the reason for that now is because these right rectangles, and again, I wasn't going to draw the whole thing right here, but in terms of the actual curve itself, probably should have done this first, but we're kind of hitting these 2 points right over here, and the curve is looking something like this. Now, I drew rectangle 1 and rectangle 2 way too high there. Sorry, guys. But here's what this would look like now. Rectangle 3 would do something like this. This would be rectangle 4, looking like that. Rectangle 5 would be right here, and I feel like I should go back and change these two because they're so bad. Sorry about that. I don't want to confuse you guys with what this actually looks like. So rectangle 2 is going to be right there, and rectangle 1 actually has some height to it. Now what I want you to notice is when we add the areas of these 6 rectangles, now there's area right here that we are counting. It's part of the areas of the rectangles that isn't part of the area underneath the blue curve. So it seems kind of logical to me to think that the approximation we just came up with right here, what did we just say, that R of 6 was equal to, I think, 11.375, that value right there is probably too big or too high for our approximation right there, as opposed to the answer we came up with a moment ago, where 6.875 was probably too low of an approximation. So what does that tell us, guys? The true answer is probably somewhere in between those two values. So what can kind of split the difference between a left endpoint approximation, which in this case, although not always, was too low, and a right approximation, which was too high? How about we start talking about a midpoint approximation? So let's get working on this one. And again, I don't want to redraw the entire figure, but I do want to draw, really, for now anyway, just the x-axis to give you guys something to kind of latch onto. My hope is, though, we won't need to do this very often. So, just like always, we're beginning this thing in this case at 0. That's also known as x naught, and that's also known as your a value. And we're ending it, in this example, at 6, which is x sub 6 or x sub n, both are the same, and we end that thing at b. And again, our partitions right here, we're cutting this thing. Nope, I did that again. Doggone it, that 6 isn't a 6, it's actually a 3. All right, so we're at a 1.5 or 3/2 right there. Right here we're at about a 1/2. Here we're at about a 1. This is roughly a 2. And over here somewhere we're at 5/2. So those are the same 6 subintervals we've used on all 3 of those problems. They haven't changed at all. But now, guys, let's talk about this first subinterval right here that starts at 0 and ends at 1/2. Now, I tell you what, let me learn my lesson from what I screwed up on the last problem. Let me go ahead and draw the curve here. It ends up here at the point 39, starts at the point 0, 0, and so this curve probably, looks something like that. Now, when I go to draw the first rectangle now, going from 0 to 1/2, I'm not using the left endpoint. I'm not using the right endpoint. I'm using the midpoint of this subinterval right here to go up, hit the curve, and that determines the height of this first rectangle. And I tell you what, I'm going to draw maybe the 5th one over here because I think that's going to be a little bit easier to see. Rectangle 5, we would need the midpoint right here. I go up until I hit the curve right there, and that is the height of rectangle number 5. Okay, looking something like that. So this is how we make midpoint rectangles. So the question then is, what is this x value right here? Or eventually, what's this x value right here where we actually determine the heights of the rectangle? All right, so let's get to that. Our general formula here, guys, is going to be m sub n. All right, a midpoint approximation with n rectangles. Well, the good news is the width of each one of these rectangles hasn't changed. It is still going to be our generic delta x value, just like it was in the last 2. But now, where do we have to evaluate the function in order to get the height of the first rectangle? Well, we're going to introduce a new notation right here, and your book tends to use a c value here. I've used m before, but you know what? I should probably be consistent right here. No, you know what? I am going to go with m right here. So I'm going to call this value M1, the midpoint of the first subinterval. And then right here, the midpoint of the second subinterval is M2. This one is going to be M3, and so on and so forth. So we evaluate the height of the first rectangle here as f of M1, the midpoint of the first subinterval. The height of the second rectangle comes from evaluating f at M2, the midpoint of the second subinterval. Plus, all right, I think you get this one, f of M3. We'll put the dot, dot, dot right now. And then the important question, anytime you do a dot, 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 is where do you end this thing? Now, all right, what's going on right here? So this one isn't hard to count out. There was M3, this would be M4, this guy right here would be M5, and the last one we want here is M6. But that's only because in this particular example that we're drawing, we're dealing with 6 subintervals. More importantly here, guys, if you remember this x, this 1/2 value right here, let me do that in purple. Those x values are what we called x1, this was x2, x3, x4, and x5. And what I want you to notice is m5 is the value right before x5. m4 is the value before x4, so on and so forth. So this one right here in this example was x6, and M6 was before that. But if in a general sense that last spot right there is x sub n, this midpoint is going to be m sub n. So that's what's got to go here. You end this thing at f of m sub n, and that n value is going to change on every problem that you do here. So I don't want you to get married to the idea that n has to be 6. So I'm going to box that formula up right there, guys. That's how you would do a midpoint approximation. So back to this problem right here. Let's get to it. Let's come up with an approximation for m sub 6. Okay, the delta x hasn't changed. That is still going to be a 1/2 in this problem. And now the height of the first rectangle comes from evaluating f at the first midpoint. The midpoint of the first interval is halfway between 0 and 1/2, which hopefully we can look at and say, oh yeah, that's going to be a 1/4. Let's do the next one together. Plus f of, let's find the midpoint of the second subinterval. That goes from 1/2 to 1. The midpoint right there is going to be 3/4. And I want to stop right here and just point out something really, really important. In the last 2 problems that we did, the jump in these x values right here, from 1/2 to 1, from 1 to 3/2, and so on and so forth, is equal to this value right here, 1/2, your delta x. The same thing happened here in the L values, okay? Does it happen here with M values as well? From 1/4 to 3/4, sure enough, that is a gap right there, a jump of 1/2. So that's exactly what's happening right here. So our third rectangle would have a height of f of, let's add 1/2 or 2/4 again and get f of 5/4. Okay, plus we'll do a dot, dot, dot right now. We know the next one that I'm not going to write would be 7/4. The fifth one would be 9/4. The last one we should have then would be 11/4 right there. And let's just make sure that seems right, guys. If this was 3 right here and this was 5/2, all right, that would be what? 2.5 right here and 3. So this would be 2 3/4. 2 times 4 is 8 plus 11. Yep, sure enough, that's 11/4 right there. That's where we wanted to leave this one off. So I would go to my calculator right now, and unfortunately, there's not a cool trick for this guy right over here, so I'd have to type all this in by hand, and I want to do that with you guys. So a 1/2 times, and here we go. So we've got an F1 of, the 1/4 would be a 0.25, plus, here we go. We have an F1 of, adding a 1/2 to that, it's going to be a 0.75. All right. Plus, what's next then? We have an F1 of 1.25 for the height of our third rectangle. Plus, come on. There we go, f1 of, and we're going to go 1.75 right there, almost there. Plus, then we have an f1 of, our fifth rectangle's height gets measured at 2.25, and then the last one we're going to have here, guys, is going to be an f1 at, and a 2.75 is where we're going to end this thing. Now, I'm hoping we're going to end up with an answer right here that's in between the previous two answers that are still on this screen right now of 6.875 and 11.375. And survey says 8.9375. So let's write that one down. 8.9375. Remember, guys, at this level, we only round to 3 decimal places, but for 1 extra place, we have an answer that's completely accurate, so I'm going to write that down. And that is pretty close, I think, to what we expected in between. In fact, I kind of wonder if I took the average of those last two answers that we came up with right here. If I took 6.875 and added that to 11.375, the first two answers, and hit enter, and then divided that sum by 2, all right, 9.125 would have been the average of those two. My 8.9375 is pretty close to that. All right, so that's how we would kind of come up with approximations right there for both a left method, a right method, and a midpoint method. Now, what's a little bit tedious about this is how difficult it was to type this mess into the calculator. And you can imagine it could get even worse if I gave you more rectangles, like if there were 8 or 10 or 12 rectangles. So eventually, we're going to start learning a way to do this, everybody, that uses a little thing you guys have learned and probably not liked very much in the end, and that would be a summation, a sigma notation right here, that's actually going to enable us to do this calculation much, much faster in the calculator rather than typing all that in by hand. But we're going to save that for another time. For right now, it probably won't kill you to type all that in one piece at a time. And if it does, I'll apologize. My bad. All right, guys, I'm going to wrap this video up right there. That's a good place to stop, and I'll come back and do the third and final leg of this video as we're going to start doing a couple of other things here a little bit later on. Yeah. Okay, sounds good, everybody. Good luck.